So now the question is, how do we show asymptotic stability? So we have these definitions that require boundedness of solutions, they require convergence. But what about the case where, for linear time systems, it's we showed that it's pretty easy to find the solution to a system. But what if we don't want to or don't need to? How do we still show that for maybe more complex systems, that our solutions are to have these properties? So that's where this brilliant notion of linear system, Lyapunov stability theory comes from. This can be generalized for nonlinear systems, but it's also works for linear systems. So this will be Lyapunov. And if you pursue a graduate degree in control theory, you'll become intimately aware of Lyapunov stability. So Lyapunov stability for linear systems. All right, so what this basically says, do I have the definition here? No. But if we consider a function v, which is defined on Rn, so the solution space of our system, and maps it to real numbers greater than or equal to 0. Okay, such that v of 0 is equal to 0. V of x is positive. Okay. V of x goes to infinity. So as you increase x, v also increases as x goes to infinity, or the norm of x goes to infinity. And lastly, if the derivative, and this is the crux, if the derivative of the Lyapunov function with respect to x is less than 0, okay? So then let's say the origin is asymptotically stable. Okay, so now for the particular case of a linear time system, so if we consider the case of x dot is equal to ax, okay? Or we can consider x dot is equal to ax plus bu with u equal to kx. So we have state feedback. This will imply that we have x dot is equal to ax plus bkx, right? We've seen this before. And this is equal to a plus bk. So it also applies for this. So if we call this guy a tilde, then we can still use this guy. So let's consider a particular function v. So note, and this is always the hardest part of all Lyapunov stability, is figuring out what this v is here. It's always the hardest part, but a great place to start is just considering just a quadratic equation. So by quadratic equation, for like a lot of physical systems, you can consider maybe the energy equation is a good place to start, or just a general quadratic equation. So by quadratic equation, so if we consider the case of a linear system and a function v is equal to x transpose px, where p is positive definite and symmetric. Okay, so positive definite, p greater than 0, means that all eigenvalues, or one way to show that p is positive definite is that all eigenvalues are positive of p. And symmetry is, right, p is equal to the transpose of p. Great. So for this function here, let's check the conditions above. So the first one is v0 equal to 0. So let's see what this looks like here. So this will be vx, again, is equal to x transpose px. So then we got v of 0 is equal to 0 transpose p0, which is equal to 0. Great. Check. Okay, so the next one is making sure that the solution is positive for all x. Okay, so f of v of x is greater than 0 for all x. So v of x is equal to, again, p transpose x. So we have that p is positive definite, right? So that means that all eigenvalues of p are greater than 0. So that's not going to contribute to any negativity in the system. And then we have that x transposes x. Let's say p is the identity, right? Which is a positive definite matrix. Then we get x transpose x. So this is very similar to just x squared, right? So it's actually x squared of all of the elements of x. So this is also positive. So if we take any value of x, just like you would square any value of a scalar, that's always a positive number, right? So this is always greater than 0 for all x in Rn. What's next? Let's x goes to infinity as the norm of x goes to infinity. Okay, so let's see. So we get x goes to infinity as the norm of x goes to infinity. Okay, so let's think about this one. So again, let's rewrite our equation here. X px. So now as we increase the norm of x, as we increase the norm of x here, what's going to happen to v, right? Well, it's also going to explode. So this goes to infinity as x goes to infinity. All right, and lastly, v dot. Okay, so this is usually where our sufficient conditions tend to come in. So how do we find sufficient conditions to get asymptotic stability? Okay, so what is v dot first? So we need v dot to be less than 0, right? And we got v here again, x transpose px. Now we got to look at x v dot. Okay, so v dot will be x dot transpose px plus x transpose px dot due to the chain rule, right? So we can take a step back here. Erase this. Take a step back here and say we want x transpose px dot, which is equal to okay, so now we got what is x dot? Well, that just comes from our system, right? So our system is x dot equals ax. So now we just plug in x dot here. Okay, so that gives us ax transpose px plus x transpose p-ax. All right, so this is, oops, trouble lining it up. All right, so then this implies that we get x transpose a transpose p x plus x transpose p-ax, which is equal to x transpose a transpose p plus p, oops, let's try that again, p-a-x. All right, so this guy right here, this needs to be negative, okay? So this means that if we can show that this guy is negative definite, or equivalently, if there exists a Q positive definite and symmetric such that A transpose P plus A PA is less than negative Q. So remember, A comes from our dynamics of our system. I could include a controller, it includes the state matrix. P is the positive definite symmetric matrix, and Q is also a positive definite symmetric matrix. So if there exists a Q, a negative Q, such that it's upper bounding this A transpose P plus PA, then, so if we have this, then we get that V, that the derivative of V is less than x negative x transpose qx. Right. So now the sufficient condition of our system is if there exists P and Q such that this holds, that this A transpose P plus PA less than negative Q, if there exists a P and a Q such that this holds, then we can show that we get negative, that our Lyapunov function is decreasing. The derivative of our Lyapunov function is decreasing, which then implies asymptotic stability. So the last part of this is that if there exists this guy, then this implies that the equilibrium point is asymptotically stable, which is generally the goal. All right. So next time we're going to talk about a couple of examples.